In today's lecture, we will be discussing slope fields for differential equation. To begin with, let us consider a differential equation given by derivative of y with respect to x equals to f of x comma y. So here we also have to specify the initial conditions. Y calculated at x equals to x0 gives us the value y0. So here dy over dx, this is the slope, and here we are saying that the slope is given by this function, which is a function of x and y. Then what we do, with the help of slope field, we can predict the solution curve, because the solution to this differential equation will be given by y as a function of x. So when we draw the solution, the slope field, then from that slope field we can predict what's the solution is going to look like. Meaning, what we'll try to do, we will have our axis, so we will have the x-axis and the y-axis. All we need to do is, once we have this particular function, we will plot a graph for the slope field. So that means we'll have to take the xy values including f of xy. For each of the values of x and y, let's say we consider x as 0, y as 0. So we will find out its particular value by particular value of the slope by plugging this value into our equation of f, x and y. So it's going to give us some values, and for that value on this location we are going to draw a slope. The slope can be sketched by using a small dash. So if it is a slope of 0, so we will draw a small dash which will be parallel to the x-axis, meaning that it has a slope of 0. If it has a slope of 1, then it is going to be slanted, just like it's in, if we extend it, then we will have a line whose slope is equals to 1. Only what we are doing, considering a very small portion slope to sketch a slope field. Depending upon the value of the slope, we will draw different slope fields which will populate the entire xy plane, and looking at the slope field, we can predict a solution for our differential equation. To better understand this, let's try out with the help of an example. We have a differential equation given by derivative of y with respect to x equals to x. We also need to specify its initial conditions. Let's say at y computed at x equals to 0, the value is equals to 2. We'll come to that in a moment, but first what we'll do, how to plot the slope field. For that we'll consider a few points on the xy plane. So let's tabulate these values. Let's take the points x and y, and we'll also plot the points for the corresponding x and y value in f of x and y. So let's say x is 0, y is 0, then f of xy, which is given by x, so this will be 0. Here f of xy is actually x, so all the values we choose for x will become the equation for that slope field. Right. So if we take x to be 1 and y to be 1, then fxy will be 1. If this is -1 and +1, this is going to be -1. If we take 0, 2, this is going to be 0. For values 2, 1, it's going to be 2. -2, +2, it's going to be -2. And let's say we take 1, 3, it's still going to be 1. Right. Now what we'll do, we'll try to sketch the slope field. For that, all we need to look is at the individual points. So let's say at the origin we have 0, 0. So we are at the origin. So this is the point of origin. We draw a small dash line whose slope is 0. Since this is 0, so this will be a simple horizontal dashed line. Then we'll go to the next point where x is 1 and y is 1. That means we are at this particular point where x coordinate is 1 and y coordinate is 1. At that point, our slope is 1. So we will represent it with a slanted dashed line. Let's go to the next point, -1. So x is -1, y is 1. Here we have a slope of -1. Then we go to our fourth point, 0, 2. So our x point is x value is 0 and y coordinate is 2. So this will be this point. Here the slope is 0. So we represent it using a horizontal dashed line. Coming to the next point where the x value is 2 units and y value is 1 unit. So this will be the point. It has a slope of 2. Now we have a slope of 2. That would mean that this will be more slanted towards the y-axis. Then we go to -2, 2. So -2 and 2. So this will be the point. So here we have a slope of -2. So this is the -2. And finally, we have x value 1, y value is 3. So here we have a slope of. So if we populate this entire plane, xy plane, with tangent lines, then we'll see that along the y-axis, which is the line x equals to 0, here at every point we'll have a slope of 0. So this will have horizontal dashed line along the y-axis. If we consider the line x equals to 1, this is going to be the line x is equals to 1. Here the slope is always going to be equals to 1. So we will draw small dashed lines with a slope equals to 1 along the line x equals to 1. We can continue for the next line. Here we have slope of 2. So along the line x equals to 2, we will have slope of 2 at each point. We can continue for the rest of the points as well. So this is going to be the slope field for the given differential equation, derivative of y with respect to x equals to x. Now, if we try to analyze this particular graph, what we'll do, we will join these tangent lines, and this joining the tangent lines, this is going to give us the solution curve. So let's say if we join along this particular line, then it has a shape similar to a parabolic function. So we can take different slope lines and we'll try to join them. So here we clearly see that what we are obtaining here is a parabolic function or a system of solution with parabolic graph. And indeed, when we solve this differential equation, this gives us y equals to x squared over 2 plus 2 for this particular initial condition. So this initial condition is when x equals to 0 and y equals to 2. So this solution curve must pass through this particular point, and the equation of this, we use a different color. So this is our graph, which is a parabolic function, and it has a equation exactly given by y equals to x squared plus 2. So this is how, with the help of slope fields, we can predict the solution of a given differential equation. Let's try one more problem. This time we have the differential equation dy over dx equals to y. That's going to make a huge difference here. So we'll begin with, we will tabulate some points. So we'll consider the x, y coordinates, x and y coordinates, and its corresponding slope function. So here, since the slope function f of xy is y, so this will be exactly the same value as y. We can take 0, 0, 0, 1. Let's take 1, 0, 2, 1, 2, negative 1, negative 1, negative 1, and 3, 2. Fine. So this will be 0, 1, 0, 1, negative 1, negative 1, 2. All I've done is picked up the values from dy. So because these are exactly the same. So we'll consider the first point, 0, 0. That means we are at the origin. So here the slope value is 0. So this will be denoted by a dashed line which is horizontal, and meaning it has a 0 slope. Let's go to the next point, 0, 1. So 0, 1 means the x value is 0, y value is 1. So we are at this point. So here the slope is 1. So we'll consider a slanted line here. And let's go to the third point here. X value is 1 and y is 0. So we're at this particular point. So here we see that the slope is 0. Let's go to the next point where x is 2 units and y is 1 unit. Here the slope is 1. Then we have 2, negative 1. So x is 2, y is negative 1. So here we have a slope of negative 1. Then we go to negative 1, negative 1. So that means here x is negative 1, y is negative 1. So this is going to be the point. This has a slope of negative 1. And at x equals to 3, 1, 2, 3, y equals to 2. So here we have a slope of 2. So this will be more slanted towards the y-axis. And we can see here that this x-axis is actually, this is the y-axis. Here the x-axis is also the line y equals to 0. So this is the line y equals to 0. Along this line, the slope is always going to be equals to 0. So at every point along this line y equals to 0, we'll have a slope of 0. If we consider this particular line, so this line is actually going to be y equals to 1, and along this line, the slope is always going to be 1. If we go 1 unit below the y equals to 0 line, then here the slope is always going to be negative 1. So at each point along the line y equals to negative 1, we are going to have a slope of negative 1. If we go 2 units above the line y equals to 0, we are on the line y equals to 2. So here at each point, the slope will be 2. So we can complete the graph in this fashion. It's much better if we use a software, because with the help of a software, this will plot out the slope field in a much faster fashion. Because doing it by hand is very tedious, and if this function becomes very complicated, then it's another story. Now what we'll do, we will try to predict the solution to this differential equation. So here, of course this is not going to be very evident, but if we have more and more points, the solution is going to have this particular form, and there will be one straight line which goes along this is not visible, so this is going to go along the line y equals to 0. That's because when we solve this differential equation, then it gives us y equals to a, which is a constant of integration, times e raised to the power of x. So here we're not considering an initial value problem, we are considering a general solution. That's why we are going to get a family of curves. So we will get some family of curves. Here, if a is positive, y equals to positive a e raised to the power of x. So these are going to be represented by the curves above the line y equals to 0. This is a growing exponential. If we consider a to be less than 0, then we have y equals to negative e raised to the power of x. This is also going to be increasing exponential, but it is going to be mirrored. It's going to be flipped about the x-axis. So this is going to give us all the family of curves which is increasing in the negative y direction. And if x is 0, then we get y equals to a, which is the straight line passing through the origin. So here a is also 0. Supposing that a is also 0, so we have y equals to 0. So you can say with the help of slope lines, we can actually predict the solution to a given differential equation. So let's try out another one. So here I'm using an online graphing calculator, GeoGebra, to plot the slope field. So let's say we started out with dy over dx equals to x. So this is going to be how the slope field look like. We can increase the density as well, or we can decrease the density, and the graph will look like this. We have a solution which we obtained was in a parabolic form. Then we considered the second problem, dy over dx equals to y. So this is what we got obtained for the graph of dy over dx equals to y. Now we will consider x divided by y. So this is the graph of x divided by y, and looking at the slope field, we can predict what is the graph of the equation is going to look like. So we can increase the density. More the density, that means there are more slopes that are being plotted on this graph. It becomes less obvious. We'll keep the density around 40%. So if we predict the solution, so this is going to give us this. So this is actually a hyperbolic function. So here this graph is not showing us the solution below the x-axis. Now this, if we complete the graph, then this is the family of hyperbolas. So this is how, with the help of slope fields, we can predict the solution to a given differential equations. See you in the next class.